Today I'm going to present the paper Ambrosia, providing performance virtual resiliency for distributed applications. First is today's roadmap. First, I will do a brief introduction of the resiliency and distributed system today, and then is the distributed resiliency solutions for today's applications. After that, I will introduce the architecture, the features, and the practice of Ambrosia. Now let's start. Today's distributed programs are very complex during dealing with failure, especially when the distributed components are stateful. The clients or the servers may fail, or they must fail, because typically a distributed system contains hundreds of or thousands of clients and servers. The hardware failure or the network issues between the servers or clients are really common to see. And the current solutions are very complex or error-prone or difficult to make applications reliable. So programmers, application developers need a general-purpose solution. This general-purpose solution have the following features. First, it is virtual resiliency, which means the solution can automatically heal the system after some failure happens. The second thing is non-determinism. The solution should have the ability to deal with non-determinism. For example, a stream of user input is non-deterministic because you cannot predict what kind of input the user will put into your system. And also, generating timestamps is regarded as a kind of non-deterministic input because you cannot predict what time is it now. Only when the user sends you some requests, and you will know, oh, the current timestamp, and return the timestamp to the user. And the third requirement is machine or language heterogeneity. This is because the applications always span different devices and programming languages. For a general purpose solution, it should be run on multiple machines or implemented using multiple programming languages. And the last but very important thing is the performance. There must be some trade-off between virtual resiliency and the performance. So the performance should be reasonable. You must not want your application to be virtual resiliency, but it is really slow to respond to users' requests. Now I will introduce the distributed resiliency models nowadays, using stateless compute, just as this figure 1. You can see from figure 1 a typical configuration for a cloud application today. First, a client records its service requests in some event hub. And then the application logic is called on batches of requests. Here, the service logic is represented as some HU functions. And any output, such, for example, this is a service chain, and you have to output your response to another service. So any output is sent to other durable queues. Finally, this pattern is potentially repeated. The infrastructure guarantees that every function will run to completion exactly once on every input. while multiple failed attempts may be made. And also, every call must begin by retrieving all application states necessary to process the request and write the state back after processing. And the developers should write code to do recovery because the infrastructure itself does not provide the ability for recovery. So we can see the disadvantages here. HU functions are stateless, while the application should be resilient. Second, the function may fail and be retried at any times before succeeding. And also, we face another challenge, that is to get a higher throughput. Because partition the application into independent identical pipelines, which may be run in parallel. This is one solution. But consequently, these applications typically store their state in a key value stores keyed on the partition ID and present the requests in batches for each partition, which makes the whole systems very complicated. So we would like to find a general purpose solution, which is proposed by the authors of the paper, that is AMBROSIA. Now in this section, I will introduce the architecture of AMBROSIA. But first, I will have to introduce a concept called virtual resiliency. It means that a distributed platform capability, virtual resiliency is a distributed platform capability which enables developers to produce applications whose behavior other than performance are unaffected by failure, but affected by where developers write failure-oblivious code. Virtual resiliency is supported through a combination of logging and language idioms which make the application deterministically replayable, as well as automatic reconnection protocols which ensure that disconnected or recovered components may reconnect and continue as if failure did not occur. It means that a failure may occur just as in the real world, but the system can work as normal after the failure happens. Now, this figure 2, is a brief introduction, or is an overview of the AMBROSIA's architecture. The architectural components of AMBROSIA are called immortals, and in figure 2, there are 2 immortals connected together. For the immortal, any AMBROSIA immortal can make RPC-style requests of any immortal it is connected to, including itself. This means an immortal is just a server as well as a client, just like a rough node. A rough node may send out append entries requests to other nodes and may receive request votes RPCs from other rough node. The immortals are just the same. It can send out requests as well as receive the request. And the second thing is that each immortal is composed of 2 running processes, which are expected to run on the same virtual machine or container or a physical machine, meaning that they fail and recover together. And the third thing is that the 2 processes communicate through local TCP connection, or in Windows, these 2 processes will use fast TCP loopback. And the first process is the immortal coordinator, IC. It will handle all log interactions. It will communicate with other immortals. It will orchestrating immortal recovery and pass messages in the form of byte arrays. And the IC relies on common runtime for applications. It is an open source virtualization layer. It uses CRA as an application hosting layer. When an immortal fails and restarts, all previously connected immortals will be automatically reconnected. And also, the fully resilient behavior is guaranteed by AMBROSIA specific sequence number. The second process is divided into binding and application. First, AMBROSIA binding. It will interact with the immortal coordinator, and it will recover from and generate checkpoints, and it will provide a state serializer. The application will execute application logic in response to requests in a deterministically replayable manner, which means that the application is actually what developers will put in, and the AMBROSIA binding and the immortal coordinator, those two components are implemented by Microsoft, and it is a part of the architecture of AMBROSIA. Also, the application process being deterministically replayable, it must hold the contract that from some initial state, any execution of the same request in the same order results in both an equivalent final state, as well as the same outgoing request in the same order, which is a explanation of the deterministically replayable manner. As I have said previously, one requirement of AMBROSIA is machine and language heterogeneity. For machine heterogeneity, since ICs pass untyped byte arrays, it is the language binding layer's responsibility to interpret these messages. Second, the machines with varying operating systems and architectures need only to agree on the serialization format of these messages to communicate successfully. So this ensures the machine heterogeneity. As for the language heterogeneity, since the IC is serialization format oblivious, as long as two language bindings agree on an argument serialization format, such as protobuf, they may successfully invoke each other's RPC calls. For example, a server and a client both agree with a same PB file, and then the server can implement this PB file using Java, and the client may invoke the method described in the PB file in Go or Python or C++. So you see, this is how the language heterogeneity is ensured in AMBROSIA. Then is the immortal coordinator design part. First, the method call is made in the application code and passed to the language binding. You can see from figure 3, step 1, M stands for message or method call. This method call is there is an arrow between the application and the language binding. It shows that the method call is passed to the language binding. Then language binding serializes all the arguments and adds the result to a queue of page buffers for later sending. And also, after serialization, the entire message is considered one big byte array, and is not interpreted until the language binding step in Immortal 2, that is step 8. And also, you can see from figure 3 some triangles. This represents a byted array. Then step 3 is about the method call passed to IC1. And in step 4, IC1 looks at the destination of each message in the batch and adds it to the appropriate output buffer. Here you can see from the figure that besides of the message M, there is a S. S stands for sequence number. S stands for the sequence number associated with the message. The sequence number is associated with the outgoing connection and will increase monotonically with each message. As a consequence, the association of sequence number is the same for both IC1, for both Immortal 1 and Immortal 2, and is independent of batching decisions. The fifth step is that the batch is sent to IC2. The sixth step is that the IC2 adds the received batch to a buffer, which serves as a log page. Then, in step 3, the buffer page is flushed to disk. The sequence numbers are recorded as part of the log record, which enables a recovery immortal to know how much input has been consumed, which is important in establishing correct reconnection. Then, the step 8 is that after the log page has been flushed, the message is sent to the language binding and the sequence number is sent back to IC1. This is because we have to prevent the creation of side effects. Then step 9 is about the sequence number is sent back to IC1. Step 10 and step 11 is that the IC1 flushes these sequence numbers and the log pages are flushed into disks. Why the Immortal 1 have to know the sequence number? This is because if the sequence number is not sent back to Immortal 1, then the output buffer in IC1 for the connection to IC2 would grow infinitely because it could not release the buffer pages until it knows that the content had been flushed to IC2's disk. So this sequence number sent backwards enables the IC during recovery to discard output produced during replay which consumers have already durably consumed. Then for the checkpoint, checkpoints are periodically taken. When the log file exceeds a particular file size, a new log file is started with all records which follow the checkpoint. Checkpoints will contain both serialized application state as well as Immortal coordinator state, which includes the state of all send and log buffers. To make checkpoint without associated loss of availability, the primary simply starts a new log file without taking a checkpoint, and one of the secondaries is used to create the actual checkpoint. Now, let me introduce impulses. Impulses are used to deal with source of non-determinism. Previously, I have introduced the architecture of Immortal coordinator. but immortal coordinator is everything about deterministic. Impulses are special RPCs that can only be called on a fully recovered and operating immortal instance, which means that impulses cannot be made during recovery. When receiving an impulse call, the arguments are recorded in the log before execution and will be replayed during recovery. And also, impulses are logically executed at most once, which means that the impulse will be lost if an immortal that collects and sends an impulse fails prior to transmitting the impulse to the receiving immortal, or when both the sender and receiver fails before the impulse is made durable, then this impulse is lost. So we have to keep track of 2 sequence numbers instead of 1. We have to keep track of the total sequence number and the replayable sequence number, which is equivalent to non-impulses sequence number. The protocol that I'm going to introduce later has the following behavior. First, all non-impulses are faithfully executed exactly once in the proper order. Second, all impulses which are locked are executed exactly once in their proper order. Third, all impulses which are not locked are lost. Fourth, all impulses from a recovering sender which have not already been sent to a receiver are lost, including checkpointed impulses in send buffers. Now, let me introduce the protocol in detail. The impulses in recovery begins by restoring the last checkpoint, and then it will clean all impulses out of all restored send buffers. This enforces the force behavior, and it will retrieve both total and replayable sequence numbers. After replay, during reconnection, the receiver sends both the replayable and total sequence numbers to the sender. The sender then begins replay from the call following the last received replayable message and sets the total sequence number for the message to the received total sequence number plus 1. In this manner, the receiver will receive the first call following the last received, and the sequence number between the sender and receiver are made consistent. Note that the sequence number consistency protocol described above is only for reconnecting for the first time after recovery. When reconnecting in other situations, such as after a TCP connection failure, sequence numbers are already consistent and the sender just starts from the messages after the last received. Then I'm going to introduce the features of Ambrosia, including high availability, time travel debugging, retroactive code testing, and live service upgrades. The first thing is high availability. At any given moment, there is typically one primary and multiple secondaries. The primary will produce the log and is connected to other immortals, and secondary will consume the log in recovery mode until they become primary. And leader election is simply the result of all instances continuously trying to acquire the exclusive write log on the log file to become the primary. When an instance acquires the lock, it becomes primary. But this typical design is not of high availability. In Ambrosia's implementation of high availability, The checkpoints are generated by a secondary, such that each time a new log file is started, there is an associated generated checkpoint which contains the state of the immortal instance at the start of the log file. So this secondary-based checkpointing prevents loss of primary availability. A new secondary then starts from the latest checkpoint and rolls forward until it is caught up. The second feature is time travel debugging. Ambrosia uses checkpoints and log files, which makes time travel debugging possible. Developers can fetch the log and checkpoint files and specify which checkpoint number to begin recovering from. All the usual debugger features may be used, such as setting breakpoints, stepping through the code, etc. Since the log is deterministic, so the same application behavior may be replayed and debugged as many times as desired, even against a live log. So Ambrosia will support time travel debugging by using checkpoints and log files. The third thing is retroactive code testing. This feature, the argument for this feature is simply same as time travel debugging, because developers can perform time travel debugging using the updated version of the application to find a bug or test a fix. Because the replay is deterministic, so the behavior can be replayed on the new version of application. The last feature is live service upgrades. This is because Ambrosia allows developers to define an upgraded immortal where both old and new versions of the application code are present in the process. When a recover happens, Ambrosia will use old version of the service. When a constructor happens, it will use new version of the service. When it has to generate a new checkpoint, it will use new version of the service. So as you can see, only recover will use the old version of the service, and as time goes by, the whole services will all use the new version of the service, and all the instances of the old service will be queued, and the new version will become primary, and the server continues as being upgraded. Now I will introduce the practice of Ambrosia. First is a real application using Ambrosia, and there were two experiments done by the author of the Ambrosia paper. One is the throughput experiment, and another is a latency experiment. First, let me introduce a real application of Ambrosia. Figure 4 shows the overall arrangement of the two services. They are command submitter and command scheduler. Command submitter satisfies the overall load and simply hash partition the overall collection of machines. Each of these machines will accept user-submitted commands from a command submission service. The command submitter and all command schedulers are running in active configurations, resulting in high availability of the service. Here, non-ambrosia calls are represented by dashed lines. Ambrosia calls are represented by solid lines. Let me follow the execution of a command to introduce the whole application. Commands arrive through a web service interface, and you can see here the dashed line of C1 0 to 100 kilo. They are input to the command submitter. After a command arrives at the command submitter, it will invoke a self call to make the request durable. Here you can see a solid line from the command submitter to itself with the label C1 0 to 100 kilo. The request itself contains the command to submit and a list of machines on which the command needs to be run. Here, the C1 0 to 100 kilo means that C1 should be executed. C1 is the name of a command. C1 should be executed on machines 0 through 100 kilo. And then the partitions of the set of the machines on which the command must be run they are partitioned into several different sets corresponding to the number of immortal instances in the command scheduler. Here in this example, we have two command schedulers, so these commands are divided into two sets. The first set is C1 0 to 50 kilo, and the second set is C1 50 kilo to 100 kilo. Then each of the command scheduler machines receive the command and the associated set of a machine it must be run on. And then it will schedule the command to these specified machines. You can see the dashed arrows here. There is C1 0, C1 1, C1 2, etc. And once the command has completed, a finished message is sent to the command scheduler through a web service interface. The scheduler then updates the state of the machine schedule and running commands, and schedules the next command if appropriate. Periodically, the scheduling immortal will scan through the list of currently running commands and reissues all open requests to individual machines. This results in at least one submission of commands to individual machines maintained. The submission of requests is made idempotent on the maintained machine, resulting in exactly one execution of commands. Note that some commands can be run in parallel with other commands and others not, so it's the scheduler's job to maintain a legal schedule for each of the machines it is responsible for. And also, the schedule is part of the serializable state of the immortal, so it is automatically protected from failure. The thread which periodically scans the running commands and reissues them only runs on the primary. For instance, we don't want secondaries to reissue these commands. In the case of a lost finished message, the running command is periodically reissued automatically, resulting in a resend of the finished message without re-execution. This guarantees exactly one's execution of the command on the managed machines, regardless of failure. For example, a command is scheduled to machine number 0, and the machine number 0 executes this command and sends back a finished message. but this finished message is lost, so the scheduler actually do not receive this message. But it will scan periodically and reassign the machine number 00. It will reassign other tasks to machine number 0. But finally, this command, which has already been executed by machine number 0, will be reissued to machine number 0. So it will know that the previous finished message is lost, and then it will not do another execution, but just send back the finished message again. So exactly once execution is guaranteed. Before introducing the experiments, I have to talk about the experiment setting. For the performance setting, the authors uses two D14V2, which has 16 cores and unlimited storage bandwidth. For the price performance experiment, the author use two F2S, which is 2 cores and 96 megabyte per second to storage, and two F2S version 2, which is 2 cores and 47 megabyte per second to storage. And the experiments are done in 4 implementations. One is a non-resilient implementation using gRPC, and 2 and 3 are AMBROSIA, implemented by C# and C++, and the fourth is HU serverless, which is based on the design in section 2. So this is the experiment result for the throughput experiment. The result of the performance optimized throughput experiments shown in figure 5. gRPC without any notion of failure resiliency is significantly less performant for small message sizes than either of the AMBROSIA variations. For 16-byte arguments, it is actually more than 10 times slower than AMBROSIA. But gRPC briefly outperforms AMBROSIA a bit near the throughput limit, that is around 32,000 bytes and 65,000 bytes. But it pulls back finally, that is when the payload size reaches the maximum 262 kilobytes. So this is as expected because the throughput there's very little difference between those two threes when the payload size is reaching the maximum. For the price performance optimized, the authors compare the cost of performing throughput experiments in terms of cost per month per megabyte if they ran the experiment continuously for a month. The results are shown in figure 6. You can see that both gRPC and AMBROSIA are much cheaper than stateless compute. For gRPC, it is not a surprise because the stateless compute pipeline is resilient to failure, while gRPC is not. But AMBROSIA provides equivalent resiliency as a stateless compute pipeline. with a much easier programming model. And Ambrosia also reaches the same behavior as gRPC. Another surprising thing is that Ambrosia is significantly cheaper than gRPC for message size below 1 kilo. So you can see that Ambrosia is a very good implementation in the sense of throughput and the cost. Here is the table for the result of the latency experiments in milliseconds. The numbers in first row has the meaning that, for example, 0.9 in the 0.9 column, 7.1 in the first row means that 90% of the latency is better than 7.1 millisecond for Ambrosia implemented in C#. Okay, now you can see that the gRPC is the fastest. It has the smallest latency. This is because gRPC simply sends a message across the wire from one machine to another. Ambrosia, on the other hand, must make 2 sequential round trips to the disk. That is, Ambrosia have to flush the data into disk both in IC1 and IC2. So what we see here is that adaptive batching and asynchrony completely close the gap on throughput, but not latency. Another thing is that gRPC has a very high tail latency, which is around 60 milliseconds. These are not one-time outliers, and they occur regularly throughout the workload of the author's experiments. It likely reflects that global locking associated with gRPC periodically cleaning up resources. For stateless compute, latency is about 5 times higher than Ambrosia's in the sense of medium, but steadily becomes higher and higher as the percentile increases, resulting in 400 times higher latency than Ambrosia at 3/9, that is 0.999. Thank you. This is my presentation.